Okay, so you're prepping for those senior software engineer interviews.
Yeah.
Right. And I bet you're seeing how often they ask about how systems talk to each other.
It's a big deal, for sure.
Huge. So we're doing this deep dive to help you get that system-level thinking down pat.
Because writing good code is one thing, but knowing how it all fits together in a bigger picture, that's senior level stuff.
Exactly. We're going to cover a lot of ground here. We'll start with the client-server model, the foundation.
Yeah, the classic.
Then we'll get into service-oriented architectures and microservices.
Those are popular these days.
Oh, yeah. Then we'll compare web services like REST versus SOAP.
Big differences there.
Big differences. And finally, we'll demystify RPCs.
Remote procedure calls? Those can be tricky.
Can be a real headache. But understanding all of this, it's going to give you a big edge in those interviews.
No doubt. It shows you're thinking beyond just a single piece of code. You're thinking about the whole system.
All right, so let's kick things off with the client-server model. This is where it all begins, right?
Absolutely. This is the fundamental pattern for pretty much all software communication.
So how does it work? What are the players involved?
Okay, so you have a server. Think of it as a provider. It offers an API, which is basically a set of rules, a contract, that defines how other software can interact with it.
Like a language they agree to speak.
Exactly. And then you have the clients, these are the consumers, they adhere to that API contract to make requests to the server.
And the most common example that everyone uses every day is the web. You have browsers and web servers, right?
Right. Your web browser like Chrome or Firefox or Safari, that's your client. When you type in a URL and hit enter, your browser sends a GET request to the web server.
It's basically asking for the page, right?
Exactly. It's asking for all the files it needs to display that web page, the HTML, the CSS for styling, the JavaScript that makes things interactive, all the images.
And what about when you fill out a form online and hit that submit button?
That's usually a POST request. In this case, your browser is sending data back to the server. It's like saying, here's some information, do something with it.
So GET is for getting stuff and POST is for sending stuff. Makes sense.
Yeah, simple as that. And the API in this case, the language they're speaking, well, it's those established web standards, HTTP, the way URLs are structured, the agreed upon ways to format the data.
It's amazing how all these different browsers and servers from different companies can all talk to each other.
That's the power of standards, right? In theory, any web browser that follows the rules can communicate with any web server that follows those same rules.
That's really cool, but it's not just web browsers out there acting as clients, is it?
Nope, not at all. Think about all the apps on your phone, your native mobile apps, or the desktop applications on your computer. They're also clients.
So when my weather app updates, it's making a request to a server somewhere.
Right. It's sending a request to a weather service to get the latest data. And even within a web page, you have things like AJX. Yeah, it stands for Asynchronous JavaScript and XML. It lets JavaScript code in the browser make requests to the server without having to reload the entire page. That's what makes those dynamic interactive websites possible.
So basically anything that initiates a request to a server, that's a client.
Pretty much.
Now, when a server responds, it's not always sending back a whole web page, right?
Mm-hmm.
Especially with these apps we're talking about.
You're right. Often the server sends back structured data. JSON has become really popular for this.
JSON, what's that?
It stands for JavaScript Object Notation. It's a lightweight way to represent data that's easy for computers to parse. So the server sends back this JSON data, maybe user profiles, product details, whatever the client requested.
And the client app takes that data and does something with it.
Yeah, updates the UI, makes calculations, whatever it needs to do.
So we've got this request-response flow happening between clients and servers.
Yeah.
But things get more interesting when we realize that a server can also be a client, right?
Absolutely. This is where you start getting into more complex system architectures. A server rarely works in isolation. To fulfill a user's request, it often needs to talk to other services.
Like a web server might need to talk to a database to get some information.
Yeah, right. Or a payment processing service to handle a transaction. This leads us to the idea of service-oriented architecture, or SOA.
And then microservices, which is a really hot topic these days.
Yeah, microservices is kind of like the next step in the evolution of SOA. The basic idea is to break down a large application into a bunch of smaller independent services.
So instead of one giant app, you have lots of little ones, each doing a specific thing.
Exactly. Each microservice is responsible for a particular business capability.
So it's like taking a big company and splitting it up into a bunch of smaller, specialized teams.
That's a great analogy. And it has similar benefits. It's easier to manage, you can deploy and update each service independently, and different teams can work on different services without stepping on each other's toes.
That sounds more agile for sure. But all those moving parts, doesn't that make things more complex in a way?
It can, but it also makes the system as a whole more resilient. If one service goes down, it doesn't necessarily bring down the entire application.
Okay, that makes sense. Now, we talked about databases earlier. How are these services different from databases when it comes to handling data?
Good question. Both involve storing and retrieving information, but they do it in different ways. Databases typically offer a powerful query language, like SQL, that lets you get very specific with what data you want to retrieve.
So you can ask the database very complex questions.
Exactly. You can filter, sort, join data from different tables, all sorts of things. But with services, it's not like that. Services expose APIs, just like we talked about earlier.
So you can only interact with the data in the ways that the service allows.
Right. The service developers define the operations you can perform and the data you can request. It's all very controlled.
So it's more restricted than a database, but also more organized and secure in a way.
Exactly. Services can enforce business rules, validate data, and make sure everything stays consistent.
Okay, that makes sense. Now let's talk about web services. Is that just a fancy name for any service that's accessible over the network?
It's more specific than that. A web service is a service that uses HTTP as its communication protocol. You know, HTTP, the language of the web.
So it's like the same technology that browsers and web servers use, but for services talking to each other.
Right. And web services are used all over the place, not just for websites. Your mobile apps are probably using web services to talk to their backends. And microservices often communicate with each other using HTTP as well, even within the same data center.
So HTTP is kind of the universal language of web services.
You could say that. It's a widely adopted standard that makes it easy for different systems to talk to each other.
Now, I know there are different ways to build web services, and the material really highlights this REST versus SOAP debate.
Yeah, REST and SOAP are two of the most popular approaches, and they're very different philosophies.
Okay, so let's break it down. What's REST all about?
So REST, which stands for Representational State Transfer, isn't actually a protocol. It's more like a set of guidelines for designing web services.
Like a philosophy you said earlier.
Exactly. REST is all about simplicity and leveraging the existing features of HTTP. It emphasizes using standard HTTP methods like GET for retrieving data, POST for creating data, PUT for updating, DELETE for, well, deleting.
So it's like using the verbs of the web to interact with data.
That's a good way to put it. REST also loves JSON for representing data. It's simple, lightweight, and easy to work with. And it encourages statelessness, meaning each request from the client should contain all the information the server needs to understand and process it.
So no need for the server to remember anything about previous requests.
Right. Each request is independent. And REST tries to make use of all the built-in features of HTTP, like caching, authentication, content negotiation, all that good stuff.
So it sounds like REST is all about keeping things simple, sticking to standards, and making the most of what HTTP already provides.
You got it. And an API that follows these REST principles, we call it a RESTful API.
Okay, RESTful API.
Yeah.
Got it. Now, what about SOAP? It seems a bit more, I don't know, formal.
Yeah, SOA, which originally stood for Simple Object Access Protocol, although nobody really uses the acronym anymore, is a more structured XML-based approach.
XML, that's another way to represent data, right? Like a more verbose version of JSON.
Yeah, you could say that. SOAP messages are XML documents, and they can be quite complex. But SOA wasn't designed to rely specifically on HTTP, even though it often uses HTTP as the transport mechanism. It has its own set of standards, the WS star specifications, which cover things like security, reliable messaging, transactions, all sorts of enterprisey features.
So SOAP brings its own toolbox to the party.
Exactly. And to define the interface of a SOAP web service, they use this language called WSDL.
OUSDL.
It stands for Web Services Description Language. It's an XML file that describes all the operations the service offers, the data it expects, and how to interact with it.
So it's like a really detailed instruction manual for the service.
Yeah, very detailed. And the cool thing about WSDL is that it enables automatic code generation.
How does that work?
So a client can take this WSDL document and use a tool to automatically generate the code it needs to communicate with the SOP service. It handles all the complex XML stuff behind the scenes.
That sounds convenient. Less work for the developers.
Yeah, it can be. But there's a trade-off. All this formality and complexity comes at a cost.
What do you mean?
Well, those WSDL documents can be really hard for humans to read and understand. And SO messages themselves, with all that XML, they can be quite large, which can impact performance. And you often need specialized tools to work with SOP, which can make things more complicated.
So it sounds like REST is more lightweight and flexible, while SOP is more structured and feature-rich, but maybe a bit harder to work with.
That's a good summary. REST is often the preferred choice for public-facing APIs, where you want things to be easy to use and understand. SOP is still used in enterprise environments, where they need those extra features and reliability.
Okay, that makes sense. Now, I remember something about REST using OpenAPI or Swagger. What are those?
So instead of WSDL, which SOAP uses, REST often uses OpenAPI, also known as Swagger, to describe APIs.
And what does OpenAPI do?
It's basically a way to document the API in a machine-readable format. It describes all the endpoints, the data they accept and return, all that good stuff. And you can use tools to automatically generate documentation, client libraries, even server code from an OpenAPI specification.
So it's like a modern, more lightweight version of WSDL for RESTful APIs.
Exactly. All right, so we've covered REST and SOAP. Now let's move on to those infamous remote procedure calls, or RPCs. The material suggests that web services are actually a more modern form of this concept.
So what exactly is RPC? What's the big idea behind it?
Well, RPC has been around for a long time in distributed computing. The basic idea is to let a program on one computer call a function that's running on a different computer over a network.
So it's like making a phone call to another computer and asking it to do something.
Sort of. And the goal is to make this remote call look and feel as much as possible like a regular function call within your own program. Like you're just calling a function in the next room, even though it's on a server halfway across the world.
That sounds like it could simplify things for developers.
Yeah.
No need to worry about all the messy networking details.
Yeah, that's the idea. But in practice, it turns out that trying to hide the network like that can create a whole bunch of problems.
Why is that?
Well, a network operation is inherently different from a local function call. There are all sorts of things that can go wrong over a network that you don't have to worry about locally.
Like what?
Network connections can be unreliable, messages can get lost, delayed, duplicated, servers can go down. And when you try to pretend that none of that can happen, it just makes it harder to deal with when it inevitably does.
So it's like sweeping the dirt under the rug. It's still there, you're just not seeing it.
Exactly. And then when something does go wrong, it's much harder to figure out what happened.
So what are some of the specific differences between local and remote calls that cause these headaches?
Well, for one, reliability. A local function call is pretty much guaranteed to either execute and return a result or throw an exception. But with a network request, you have to worry about timeouts.
What's a timeout?
It's when you send a request and you wait, but you never get a response back.
So you don't know if the request got lost, if the server's just slow, or what.
Exactly. It's a state of ambiguity. And that can be tough to deal with programmatically.
And if you just keep retrying the request, you could end up doing something twice.
Oh yeah, that's another big problem, idempotency. If you make the same request twice, it should have the same effect as making it once. But that's not always the case.
Like if you're buying something online and you click the button twice because the page is slow, you don't want to end up placing two orders.
Exactly. You need to design your services carefully to handle those kinds of scenarios.
And then there's the performance aspect. Network calls are just inherently slower than local calls, right?
Absolutely. Local calls happen within the same memory space, so they're super fast. Network calls involve sending data over wires, which takes time. And the latency can vary depending on all sorts of factors.
So even if the server is working perfectly, the network itself can slow things down.
Right. And then there's the issue of data serialization.
Serialization.
It's the process of converting data into a format that can be transmitted over the network, like converting it into a stream of bytes.
So you can't just send objects directly over the network.
You have to serialize them on the sender side and then deserialize them on the receiver side. And that adds overhead, especially for complex data structures.
And what if the client and server are using different programming languages?
That adds another layer of complexity. The RPC framework has to handle translating data types between those languages, which can be tricky.
So it sounds like RPC is trying to do something that's fundamentally difficult, maybe even impossible, trying to make the network disappear completely.
That's the core issue, and that's why REST, which embraces the realities of the network, has become so popular.
But I read that RPC isn't going away. There are these newer RPC frameworks that are gaining traction. What's different about them?
These newer frameworks are more pragmatic. They acknowledge the challenges of network communication and provide tools to help developers deal with them.
So instead of trying to hide the network, they're embracing it.
Exactly. For example, many of them use asynchronous programming models with things like futures and promises.
What are those?
They're basically ways to represent the eventual result of an operation that might take some time. They let you write non-blocking code, so your program doesn't have to sit there waiting for a response from the network.
So you can do other things while you're waiting.
Exactly. It makes your programs more efficient and responsive. And some frameworks, like gRPC, support streaming, where you can send a sequence of requests and responses over a single connection.
So it's like having a conversation instead of just shouting single messages back and forth.
Yeah, a more efficient conversation. And these frameworks often use efficient binary protocols for serialization.
So they're faster and use less bandwidth than text-based protocols like JSON.
Right. They're optimized for performance. And many of them have built-in service discovery, which is important in microservices architectures where services can come and go dynamically.
So it sounds like these newer RPC frameworks are a good option when performance is really important.
They can be. But REST still has its advantages, especially for public APIs, where you want simplicity and a wide range of tools and libraries.
Okay, so it's a trade-off. Choose the right tool for the job.
Always. Now, there's one last thing we should talk about, and that's API evolution.
How APIs change over time.
Exactly. As a senior engineer, you need to think about how your services will evolve without breaking existing clients. That's called backward compatibility.
So you don't want to release a new version of your service and suddenly all the old clients stop working.
Right. And you also want to think about forward compatibility, which means that old clients should still be able to understand responses from newer servers.
So even if the server adds new features, old clients should still be able to work.
Ideally, yes. And the way you encode your data plays a big role in how easy it is to maintain compatibility.
So different data formats have different ways of handling changes.
Right. Frameworks like Thrift, gRPC, and Avro have built-in mechanisms for schema evolution. And OAP, with its XML schemas, has ways to manage changes too.
And what about REST with JSON?
JSON is pretty flexible. You can usually add new fields to a JSON object without breaking old clients. But you have to be careful about changing existing fields or removing them.
Makes sense. It's easier to add new stuff than to change old stuff.
That's a good rule of thumb.
Yeah.
Now, things get even more complicated when you have clients outside your own organization.
Like when you're providing a public API.
Yeah. You don't have control over when those clients will update their code, so you might have to support old versions of your API for a long time.
That sounds like a maintenance nightmare. How do you even keep track of all those versions?
There are different ways to do API versioning. You can include the version number in the URL, use custom headers, or even tie the version to the API key.
So there's no one right way to do it.
Nope. It depends on the specific API and how it's being used.
Well, I think we've covered a ton of ground here. We've gone from the basics of the client-server model all the way to the complexities of API evolution.
It's a lot to take in, but it's all essential knowledge for a senior software engineer.
And being able to talk about these concepts intelligently, to explain the trade-offs and the reasoning behind different choices, that's what really sets senior engineers apart.
Absolutely. It's not just about knowing the technology, it's about understanding the bigger picture.
Exactly. So here's a final thought for all of you out there preparing for your interviews. Think about REST in gRPC. Can you imagine a specific scenario where you would definitively choose one or the other? What factors would influence your decision?
That's a great exercise. Really put yourself in that situation and think about the performance requirements, the development process, the tooling available, the expertise of your team.
Because ultimately, making these kinds of architectural decisions is a big part of being a senior engineer.
It is. And the more you understand about how systems communicate, the better equipped you'll be to make those decisions.
All right, folks, that's it for this deep dive. We hope you found it helpful. Keep learning, keep exploring, and good luck with your interviews.
Best of luck.
Thanks for joining us.
It was a pleasure.